Nice. So, yeah, welcome everyone to another week's intercontinental seminar on gravity and cosmology. Today we have the pleasure to have with us Alexandra Eleni Koloniari, who's a PhD student at the Aristotle University of Thessaloniki. And she works on gravitational wave astronomy under the supervision of Nikos Terioulas. And today she's going to talk about ResGW, unveiling new gravitational wave events with machine learning. Yeah, the floor is yours.
Okay, so hello everyone, and thank you, Konstantinos, for the invitation. So, together we will talk, as Konstantinos mentioned, about the discovery of gravitational wave events with machine learning, and specifically with our code, ResGW. But let's take it from the beginning and start with some information about gravitational waves. So, how do we detect gravitational waves with the gravitational wave detectors? And the current generation of gravitational wave detectors include Virgo, the two LIGO detectors, Livingston and Hanford, the GEO600 detector, and CAGRA. However, out of all of those detectors, only Virgo and the two LIGO detectors have made a gravitational wave detection, since GEO600 has very short arm length and CAGRA hasn't reached the necessary sensitivity yet. But from 2015, that we had the first gravitational wave detection, since today we have over 290 candidate events. The vast majority of them being binary black hole mergers. And when it comes to the detector sensitivity, the two LIGO detectors have reached up to 160 megaparsec during O4, and we expect it to double in the upcoming O5 observing run. However, notice that the number that I mentioned here, the 290 candidate events, is actually higher because that corresponds to the start of O4C. Now, we will actually have even more gravitational wave detections with the next generation of gravitational wave detectors that include kit projects such as the Einstein Telescope, the Cosmic Explorer, and LISA. Einstein Telescope will be the next generation underground detector of Europe, and most likely will have a triangular shape with 10-kilometer arms. However, there are alternative single L-shaped designs that are also under study. It will also use cryogenic mirrors to reduce thermal noise, and you can see how this specific detector will most probably look like in the upper figure here. The Cosmic Explorer will be a detector similar to the LIGO detectors, meaning it will most probably have an L shape. But the length of the arms will be 10 kilometers. So we will have 10 times the sensitivity of LIGO detectors. And LISA will be a space-based triangular detector with each arm being 2.5 million kilometers in length. So we will also have sensitivity in the low-frequency gravitational waves. Now, there are a lot of different representations for gravitational waves. The most commonly used are the strain time series, or just time series, which are gravitational wave strain data as a function of time. And in this figure here, you can see the data from Hansford, Livingston, and Virgo detectors, depicted with red, blue, and purple color, respectively. And you can also see with the darker lines here, basically the reconstructed waveforms for that specific candidate event. Additionally, one more very commonly used representation are the spectrograms that are time frequency representation of the data. And in them, we basically expect that banana shape, or as we call it, the chirp. And the final representation we will discuss today is the match filter SNR time series, which are basically show how well a template waveform matches the data over time. And if we're lucky and we have a match, we will basically see a big peak like the one you can see in here. But let's dive a little more into what match filtering is. So, match filtering is a signal processing technique that compares a set of template waveforms, or as is usually called, a template bank, to noisy data to detect signals with known morphologies. And the basic steps are the following. Basically, we do perform a Fourier transformation to the data and the template, and then we compute this quantity here, in which the H tilde star correspond to the complex conjugated template, and Sn correspond to the noise power spectral density. And then we can finally compute the optimal SNR using this specific formula here. However, even though that sounds simple, and it actually is simple, we actually need to do that millions of times because we have millions of templates in a template bank. And so, which are the strengths of match filtering? Well, first of all, it is optimal for known signals and Gaussian noise, and that is actually mathematically proven. Additionally, it is easy for us to understand why it works, because basically what we do is that we have the data, we have a template, and if they match, most likely we have a signal there. And finally, it is also well established. There were decades of development of gravitational wave template banks, and there are also multiple detection pipelines, such as PyCBC, MBTA, GSTL, alias, etc., that uses this specific technique. In fact, most of the traditional pipelines do use match filtering. However, there are two sides in every coin, so there are also limitations in match filtering, such as it is template dependent, meaning it is limited to signals similar to those covered by the waveform bank because, as I said before, we look for a match. So if we don't have something similar, there won't be a match. Additionally, as I also mentioned before, it assumes Gaussian noise, but as we all know, real detector noise is not Gaussian and non-stationary, meaning there are glitches in it, and those glitches actually reduce its effectiveness. However, those aren't the most important limitations. As I mentioned before, we do expect the next generation of gravitational wave detectors, and that means that we will basically have multiple detections each day. And that is a problem when we use match filtering because it is computationally expensive. In fact, we compare data against millions of templates. So it is very slow and resource intensive, especially for long duration and high mass ratio signals. And additionally, it is also limited by per detector SNR threshold because usually match filtering applies fixed SNR threshold in each detector, such as 5.5, before coincidence checks. And what does this mean? Basically, if we have a signal that is very loud in one detector, but has low SNR in the other detector, that signal would be cut it off because of the threshold that we used in one of the detectors. So, is there anything else we can try? Well, obviously not. Not all hope is lost. There is something we can try, and since they are very trendy these days, why not try neural networks, since they are everywhere? And for those that aren't familiar, neural networks are artificial intelligent models that are inspired by biological neurons and their connections so that they can learn patterns from data to make predictions or decisions. And here you can see the smaller unit of a neural network, the neuron. And basically, those yellow circles are the inputs, and each of those inputs are then multiplied with a quantity called weight. And that weight basically represents how important is that specific input for that specific neuron. Then we add them in a sum. And finally, we add one more quantity that is called the bias, which basically moves that sum left or right. And finally, we use all that as an input in a function that is called an activation function. And that is a non-linear function that basically produces the output of that specific neuron. Then, if we have a group of neurons that are all using the same input vector and they work in parallel, we have a layer. And if we have a lot of layers that connect with each other, then we have a neural network. And we can connect those layers with different ways, and that way we can create different architectures of a neural network. And which are the strengths of neural networks? Well, first of all, neural networks sometimes can detect signals that are outside of the training template space, because it's not the same as match filtering. Match filtering, as I mentioned before, looks for a match, but neural networks are trained with data and they learn how a signal looks like. They learn their morphology. So, for example, think of it like that. If I provide to you a picture with a dog braid that you have never seen, you would most probably understand that it's a dog, even though you have never seen that specific breed again in the past. Additionally, they can also recognize non-Gaussian noise with proper training. And that means that basically, if I train a neural network by providing real noise, I can train the neural network to understand when it sees glitches. So it will most probably give less false alarms than match filtering because it knows how glitches look like. But the most important strengths are those that counter the limitations of match filtering, such as neural networks can achieve real-time detection speed. In fact, once they are trained, neural networks are actually orders of magnitude faster than match filtering. And they are also adaptable to multi-detector data. Basically, I can train a neural network by giving it data from both or 3 detectors at the same time. So they can detect gravitational waves by jointly analyze multi-detector data without requiring per detector thresholds or coincidence tests. And that means that they can detect signals that are consistently weak in all detectors, but are still significant as a network SNR. However, yes, we need to be objectives. So there are also limitations on using neural networks as well, with the first being that it's harder for us to understand why they make a detection. With match filtering, it's easy to understand because it's basically maths. Here is a little bit more complex than that. Additionally, they are dependent from the training dataset. That means that we require large, diverse, and high-quality training sets because poor training actually equals to poor performance. And additionally, they might, but not necessarily, require retraining for new detector data. If you have a neural network that isn't that adjustable and doesn't have very good generalization capability, it might have problem with different observing periods because different observing periods have different glitches, different noise level, etc. However, we will see that it's not necessary. Now, moving on, we can talk about a little bit of history, exactly because there was a need to create more rapid pipelines. Here is where the first machine learning gravitational wave search mock data challenge comes into place. And the goal of that challenge was to basically let different groups create neural networks and see if those neural networks can detect gravitational wave in a specific setup, and if they actually can compete with two traditional pipelines, the CWB, which uses wavelets, and PyCBC, which uses mass filtering. And in order to do that, there were 4 datasets created, 3 that did contain Gaussian noise with different PST variations, and 1 that did contain real O3A LIGO noise, cleaned of the GWTC2 events. Additionally, all those datasets did contain negative samples that were basically only noise and positive samples that contained noise plus injections generated by the IMR Phenomex PHM waveform model. Also, all files did include 2 groups, one for the Hanford detector and one for the Livingston detector. In this table here, you can see the parameters and their distribution. And also in the figure here, you can see the distribution of the 2 individual masses, M1 and M2, and the duration of those signals in all test datasets. And now I can present to you the results. Basically, the results were provided in terms of sensitive distance versus false alarm rate. And for those that aren't familiar, sensitive distance represents the effective range within which a gravitational wave detection algorithm can detect sources at a given false alarm rate. And it accounts for both detection efficiency and source distribution. It accounts for the source distribution because we use the chirp mass in the formula that we use in order to calculate the sensitive distance. And in here, the results of the pipelines that were neural networks are depicted with solid lines, and the 2 traditional pipelines are depicted with the dashed lines. The orange one depicts PyCBC, and the brown one depicts CWB. And as you can see in dataset 4, which is the most important dataset because it contains the real LIGO noise, the ResGW predecessor of Model 1 and Model 2, Virgo Auth model, which is here depicted with purple, actually achieved the best performance out of all the neural network pipelines. And it also achieves better results generally from CWB. And that creates a question. Can we reach traditional algorithms? Spoiler alert, yes, we can. And here is where the next paper comes into place with title Deep Residual Networks for Gravitational Wave Detection. That is a work by Paraskevi Noussi, me, Nikolos Passalis, Panagiotis Iosif, Nikolos Terioulas, and Anastasios Stefas. And here is where we introduce ResGW Model 1, which is a machine learning gravitational wave algorithm for binary black hole detection. Basically here, we did use 27 residual blocks and 54 layers in total, leading to 1.3 million learnable parameters. Additionally, we did include some innovations such as a deep adaptive input normalization, or DAIN, a dynamic dataset augmentation, and curriculum learning using an SRS schedule, as you can see in the figure here. Basically, we started the training with signals that are easier for the network to learn, so signals with higher SNR values. Then we did give the network signals with lower SNR values, and finally, we did provide all the signals for the network to learn. As for the training dataset duration, it was 12 days, and we did use real data quality noise from O3A from both LIGO detectors. And the waveform model used for the injections was the IMR Phenomex PHM. The mass range for the individual masses was between 7 solar masses and 50 solar masses, both initially uniformly distributed. However, because we do use the constraint later that M1 needs to be larger or equal than M2, the distribution we end up with for the individual masses is not uniform. And that fact, combined with the fact that there is a non-linear relation between the individual masses and the chirp mass, we end up with a distribution for the chirp mass like this one. And even though that specific distribution actually aligns with the real distribution in that specific chirp mass range, it isn't optimal to train a neural network. Neural networks tend to learn better with uniform distributions. With a distribution like this, they tend to learn better the signals that are in the middle parts of the distribution, while they tend to ignore, or they aren't trained as well, to the signals that are in the outer parts of the distribution. So we consider the effective training range to be between 10 solar masses and 40 solar masses for the chirp mass, which is also the 95% confidence interval. And here are the results. You can see that ResGW model 1, which is here depicted with a blue line, actually surpasses the standard PyCBC in this specific setup, which is the same as the one of dataset 4 of the challenge. We also do provide the variance in different test datasets because, as I forgot to mention before, all the datasets used for the challenge were 1 month in duration, and that is a very small duration in order to be able to say that you have a robust result. So that's why we did include this variance, and as we can see here, ResGW model 1 is pretty robust because we notice that there is a very small variance here. And for those that are interested, you can find ResGW model 1 here, and you can do your own tests. But now I want to insist a little bit more about the variance because it's actually very important, even when we do comparisons, even when we actually try to evaluate a pipeline. So we need to know how do sensitivity metrics fluctuate due to dataset variability. And this is actually our latest work, Robustness of Sensitivity Evaluations for Gravitational Wave Detection Algorithms. This is a work by me, Lazaros Lazaridis, Christos Paschalidis, and Nikolaos Terioulas. And here we did check two specific metrics, the number of detected injections and the sensitive distance. And in order to do that, we did create 28 test datasets in total. And we did use them in 3 different categories: datasets with identical noise and varying injections, datasets with varying noise and identical injections, and datasets with both varying noise and injections. And basically, each category did have 9 completely different datasets, and one that was common in all of them, the reference set, which was the same as dataset 4 of the challenge. However, because we did use the noise file that was used for the challenge, there were still 37 gravitational wave events from the ResGW, GWTC 2.1, EAS, and OGC catalogs present in the data, because in that file, only the events from the GWTC 2 were removed. Additionally, I also want to point out that here, when we say identical injections, we mean that in terms of parameters. However, because we do inject in different GPS times, we do have different projections. However, that is not a problem, as we will see later on. For anyone interested, the test datasets can be found in here, and you can do your own test, or you can recreate our results if you want. Now, let's go to the datasets with identical noise and varying injections. What we notice here is basically that the number of detected injections and the sensitive distance both seems to have low variance across all false alarm rates. In those plots here, you can see the number of detected injection versus the chirp mass for false alarm rate equal to 1, 10, and 100 per month. Here you can also see the sensitive distance versus a false alarm rate, just like before. And in the tables, you can see the confidence interval for the mean, the standard deviation, and the coefficient of variation for both the number of detected injections and the sensitive distance. And as you can see, for all false alarm rate, we do have pretty tight confidence intervals. So far, so good. Basically, what we can conclude here is that ResGW generalizes well across to the signal variations, because we do see that it has consistent detection rate across all different signal realizations from the same distribution. But that also means something different, that if in the later test that we will do, that we will use different noise, we do notice performance variability that would come from the noise and not from the signals. So noise is the primary source of performance variability. And that is exactly what we see with the number of detected injections. When we use varying noise and identical injections, and it is the same when we use both varying noise and varying injections, so I didn't include that here because you will see basically the same. We do notice that if we use two different test datasets, we might have two completely different results. And that is also apparent when we see the upper limit of the confidence interval for the coefficient of variation here, which is equal to 39.1%, which is a very high number. However, that is not the case for the sensitive distance. As we see here, even for lower false alarms, we do see that there are tight confidence intervals, and that is also apparent in the plot. So, which are the results here? Basically, we do notice that there is a dominant role of noise fluctuations, especially at lower false alarm rates. And we also see that the number of detected injections isn't as reliable at false alarm equal to 1 per month. And that is also apparent in the figure here. You can see the coefficient of variation versus the false alarm rate, and you can see how big the interval is. However, we might be able to use the number of detected injections at false alarm equal to 100%, but that is too high for credible detections. In fact, the performance of the number of detected injections at the false alarm equal to 100% is actually similar to that from the sensitive distance at false alarm equal to 1 per month. Additionally, I mentioned before that there were some signals still in the noise. So we did wanted to see what would happen if we would also remove those remaining signals. And what we did see is that after the removal of the remaining real gravitational wave events, the number of detected injections at false alarm equal to 1 per month actually increased by 19.2%. And that is also visible in the plot here. You can see that in the left panel that we have the contaminated noise. These were the results. And these are the results for the same datasets after the removal of those events. However, interestingly, we see that after the removal of those events, the sensitive distance at false alarm equal to 1 per month actually increased only by 1%. And that means that basically sensitive distance is still robust, even if we have some gravitational waves still in the data. And now you might ask me, Alexandra, what's happening? Why do you have such a difference in the performance when you remove those events? Well, basically, in those specific datasets, there were still nearly 10 real gravitational wave events in those data. And I need to remind you that basically, because that is the same background file I used for the challenge, many studies did use that same file that did contain those real events. There were also one of the events that were detected by ResGW model 2, and we will discuss about those 8 new detections later on. But the thing is that ResGW model 1 also did detect that same event with high rank statistics. So specifically the presence of GW190511 is what compromised the false alarm rate estimation for ResGW model 1. Different pipelines will perform different in different events. So these are the results. Basically, the sensitive distance at false alarm equal to 1 per month seems robust even under signal 1 month evaluations. However, that is not the case for the number of detected injections. If we want to use the number of detected injections, we would need to go to a false alarm equal to 100 per month, but that is too high for a credible detection. Additionally, we did see that including real gravitational wave events in noise can bias the number of detected injections, and that is possibly true for other metrics as well. So, if we want to achieve robust evaluation, that would require from us to use multiple datasets, real event removal, uncertainty reporting, diverse metric, and will also be good for the community to use standardized protocols in order to make fair comparisons and evaluations. And now we can move on to the critical test, which is the performance of real data. Because after all, I can stay here and talk to you about different test datasets and comparison of ResGW with different pipelines, but that doesn't matter if we can't actually have a good performance on detecting gravitational waves in real data, because at the end of the day, that is our purpose. So this is the paper that discussed this specific theme. New gravitational wave events discoveries enabled by machine learning. This is a work by me, Evdokia Koussouba, Parskevin Noussi, Parskevas Labropoulos, Nikolaos Passalis, Anastasios Stefas, and Nikolaos Tegioulas. And here we introduce our latest model, ResGW Model 2, and its new enhancements. With the first being that we did use a larger training dataset. This time we did use 35 days instead of 12 days that were used for Model 1. Additionally, we did use double precision floating point format, but only on the the final softmax layer. And we did that because we didn't want the process to be time consuming. Additionally, we also did that only for the data analysis. I also need to point out here that the output is in the range initially from 0 to 1. However, we did notice that in the signals, the rank statistic values were similar to 0.999999, etc. So in order for us to be able to understand our results better, we did decide to use a logarithmic ranking statistic using the formula that you can see in here. Basically, here R is the initial ranking statistic in the range between 0 and 1. And this value here is added in order to not have problems when R is equal to 1, and the minus 16 correspond to the double precision that we used. Furthermore, we also used the 350 Hz low-pass filter in both training and data analysis, and we did that because we did want to remove the high-frequency noise. And that is also very apparent when you actually look at the figure here. You can see that in the upper panel, in which we didn't use that filter, there is plenty of high-frequency noise. And in fact, you can't really see where the signal is with the naked eye. However, when you remove that extra noise, you can actually see where the signal is with the naked eye. It's actually distinguishable. And in order for you to be able to visualize where the signal is better, we used this specific dashed red line to show where the merger time is for that specific signal. Now, for the data analysis methods, we did use glitch removal techniques using Gravity Spy for both the background generation and O3 data. We also did a hierarchical classification of the triggers, and we ended up with 3 classes: the default low pass class, the selective noise rejection, and the selective passband class. And we also did a ranking statistic optimization using the mean ranking statistic. And actually, those last points were my work, and we will discuss them immediately, starting with a hierarchical classification of the triggers. Now, basically what we do is what we see here in this flowchart, but as you can see, the process is pretty complex, so I won't go into the details. What I will say here, though, is that the default low-pass class corresponds to triggers that come immediately out of the network. The selective noise rejection class corresponds to triggers that pass some noise filters, and we have a reduction of the false alarm by 61%. And the selective passband class corresponds to triggers that, besides the noise filters, pass also some frequency filters, and we have a reduction of the false alarms by 90%. Now, for the ranking statistic optimization, you see ResGW checks 1 second segment, but in that 1 second, a signal could be anywhere in it. Could be in the middle, could be in the outer parts. But the thing is that the place that the signal is changes the ranking statistic that the network gives. So we didn't want to rely in a kind of random ranking statistic, kind of random because when we run, we don't know where the signal will fall in that segment. So we decided to basically start 5 seconds because before each trigger of interest, and trigger of interest are triggers that have initially a high rank statistic. And then we would move the start of that dataset with very, very small steps. And we would take the rank statistic of the trigger we care about each time. And then in the end, we would use the mean of all those rank statistic values. And that is easier for you to understand if you see the figure here. Basically, what you see is that the light blue time series represent the rank statistic with the shifted start time of an event, and the peak time series depicts the same for representative noise triggers. And as you can see here, basically, there are some shifts for which the rank statistic of the event is actually lower than that from the noise trigger. But when we use the mean ranking statistic, the difference between the two is actually pretty clear. And you can see here the histogram of the mean ranking statistic, or as we call it in the paper, the sample average ranking statistic for the foreground events depicted with light blue and for the background triggers depicted with pink. Now, we actually do talk about gravitational wave detection. So there are two important statistics, the false alarm rate and the astrophysical probability. And basically, each pipeline has to report those two. If you, for example, go to POST to see the gravitational wave events that are detected by LIGO, you will see which events, which pipelines detected that specific event. And if you click on them, you will see that they report the false alarm rate, network match filter SNR, and the astrophysical probability with which they detected that specific event. And that's exactly what we also do. We wanted to find the false alarm rate, and in order to do that, we needed to create a background. We decided that we would create a 10-year background, and in order to do that, we did use 81 days of data quality O3 noise, then we did glitch removal, then we did perform different time shifts, and finally, we did use the hierarchical classification of the triggers. And you can see how that looks like for the selective passband class. Here, the gray dashed lines represent different noise realizations. The nonlinear larger line here depicts the background triggers in a 10-year duration. Basically, it's the sum of those dashed lines. The straight line is its fit, and the smaller, darker line correspond to the O3 triggers and has basically the same duration as those dashed lines. And you can also see the background triggers in a 10-year duration and their fits for all three classes in this specific figure. And the blue triangles are our 8 new gravitational wave detections, firstly detected by our code ResGW model 2. Now, I also mentioned that we need to report the astrophysical probability, and in order to do that, we need to find the background distribution and the foreground distribution. But let's take it from the start. Here you can see the cumulative distribution of the IFAR, or the inverse false alarm rate. And basically, what we see here, we only have the noise trigger. We have removed all the known gravitational wave events. And we see that the distribution actually falls inside those gray areas, and those gray areas represent when we expect the noise to be. Later on, we will see that when we leave those events inside, this distribution for all three classes will go out of that gray area. And in the figure here, we present the background distribution versus the false alarm rate, versus the rank statistic, sorry. And basically, we use this specific formula for all three classes, assuming that X is equal to the rank statistic divided by a constant C, which is different for each of those classes. And you can see that those fits are actually pretty good for all three classes in O3 data. Now for the foreground distribution, you can see what we talked about before. Now that we do include the gravitational wave events, all classes are out of the expected noise region. And we also used this specific formula to find the foreground distribution. In the left panel, you see the performance of ResGW in LIGO injections. And then we use this specific fit also in O3 events, and we see that actually it is a pretty good fit for O3 events as well. So by using the derivatives of those formulas that we discussed before, we can find the astrophysical probability by using this specific formula. And basically, this is what it looks like for each of the three classes, and the dashed line corresponds to the threshold 0.5. So basically, all triggers that have an astrophysical probability greater than 0.5 can be considered candidate events if they also pass some consistency test that we will talk about later. Additionally, here I also present the astrophysical probability versus the false alarm rate for all the pipelines, the other pipelines with orange, and for ResGW with blue. And the light blue X's here represent our 8 new candidate events. And now that I mentioned candidate events, I also mentioned that we need to pass some consistency tests, such as checking the arrival time. I made sure that it's below 10 milliseconds, because that is the time that light needs to travel from the one LIGO detector to the other LIGO detector, and as we know, gravitational waves travel with the speed of light. Additionally, we also did perform the chi-square test, which was also used to find the reweighted SNR, here depicted with rho hat. And we also did the parameter estimation using the Bayesian inference library BLB. Here I also present one of the corner plots for one of our new detections. And here you can see also some information about our new candidate events, such as their event name, their GPS time, their astrophysical probability, etc. I won't say much here. I will just say that our 8 events have a cumulative astrophysical probability of 5.94, and also all of our 8 new gravitational wave detections were subsequently verified by an independent parameter estimation study later on. Here I also present the QP plot of all of our 8 events, and you can clearly see the chip that we discussed about earlier. And I also present a 2 time series example for 2 of our new candidate events in order for you to see how the data of the detectors look like and how the reconstruction looks like. And you also see the 90% confidence interval depicted with light blue, and you can see that they are a very good fit. Now, I also need to provide to you some very important population properties of our new candidate events, such as that our distribution actually aligns with that from the other catalogs, and that is a very good indicator that those are indeed gravitational wave events. And secondly, our new events tend to exhibit higher luminosity distances compared to the majority of the previously published events. Our events here are depicted with the orange, red dots. And why that is important? Because basically higher luminosity distances usually lead to lower SNR values. And as we discussed earlier, the traditional pipelines do use SNR thresholds in each detector. So that is probably one of the reasons why those specific events weren't detected by other pipelines, but were detected by ResGW that sees 2 detectors at the same time. And now that we mentioned other catalogs, we need to provide to you the results of ResGW on the events of the other catalogs. So there were 43 published gravitational wave events in the GWTC, OGC, and the AS catalogs within our effective training range, and ResGW detected 34 out of the 43 with an astrophysical probability greater than 0.5. There were 9 events that weren't considered as gravitational wave events from our pipeline, but I need to point out that 4 of them actually had pretty low astrophysical probability from the algorithms that initially detected them. Additionally, there were also 55 published gravitational wave events outside of our effective training range, and ResGW detected 10 of them. And that actually shows that it has a very good generalization capability. I also forgot to point out that within our effective training range, the combined our events with the previously published events were 51, and actually ResGW seems to be the most sensitive pipeline in our effective training range, because ResGW detects 42 and the next best performing pipeline only detects 37. However, I need to point out that other pipelines were not set up for optimal search in our effective training range. Now, back to the generalization capability. We wanted to dive a little more into that, and we wanted to see if ResGW is actually good at understanding different noise that it has not seen before. So we also checked its performance on events that were detected by Virgo combined with one of the LIGO detectors, and on O1 and O2 data. And we saw that even though ResGW was not trained on Virgo data, it generalizes well when a Virgo detector is used in place of Livingston or Hanford. You can see here that it shows pretty promising rank statistic values. And additionally, it also identifies 6 out of the 8 events in its mid-chirp effective training range with its greater rank statistic value in O1 and O2 data. You can see here its greater rank statistic value is 16. So, which are the conclusions? Well, ResGW Model 2 detected 34 out of the 43 events within its effective training range, and it also detected 10 outside of its effective training range. Additionally, it shows promising performance on Virgo data combined with Livingston on Harvard detectors, and also shows promising performance on O1 and O2 data. And those last 3 points shows that it has very good generalization capability. But most importantly, ResGW did detect 8 new gravitational wave events. And in fact, it's the first time that we have machine learning-based coincident detections of gravitational waves ever. Now, for the future, we can analyze O1, O2, and O4 data with and without retraining. Additionally, we can try different combination of detectors, such as single, double, and triple detector setups. And we can extend ResGW for the offline detection of binary black hole mergers in other Mars ranges, or for example, for binary neutron stars. Now, when it comes to the gravitational wave detection of with machine learning in general, we can build shared datasets and metrics for fair comparisons, like we did in our latest job work. And we can also combine match filtering with machine learning for hybrid pipelines. And there are actually works in this direction. That's all. Thank you.
Thank you very much, Alexandra, for the very nice talk. Yeah, are there any questions from the audience? I don't see any hands, so maybe
Okay.
I can ask a couple of questions.
Okay.
So yeah, I mean, I'm more interested, let's say, not in the detection mechanics itself, but rather in, let's say, the cosmological implications. So yeah, as you said, like several uh, of the new candidate events ResGW identifies, they appear to be lower SNR or more distant systems, let's say, that weren't picked up by the traditional pipelines. So do
Yeah.
these events, let's say, extend the effective redshift reach of the O3 catalogs? And like what consequences would that have, let's say, for estimating the redshift evolution of the merger rate?
Well, there were detections from other pipelines that have similar or higher luminosity distances, so they do not change much because they are also small in number. They are only 8, so they don't change the results as much. Also, you can see that basically there are other events that have a very much bigger
Yeah, that's
luminosity
true.
distance,
Yeah,
so they don't change much.
I see.
What we can say is that we are more sensitive and we can detect more events. So that's the only conclusion, basically.
Mm-hmm. Okay. So I continue since there's no. Are there any other questions? Okay, let me ask one more. So yeah, as you said, like these candidate events, they seem to have like relatively heavy, let's say, masses, right? So like how would if we incorporate them, let's say, in the O3 population, so how would this influence the constraints on primordial black holes or other early universe formation channels, stuff like that? Do you have any idea about that?
No idea at all.
Okay,
Basically, they are in
yeah.
the middle part of the distribution here. You can say basically if we added them in that distribution, that peak would be a little bit higher, but not big of a change.
Yeah, but in general, they could somehow be, I mean, set some constraints on,
Possibly,
I
I'm
mean,
not that.
primordial black holes can be like depending on when they are formed, they can have different masses, so they could somehow, I mean, possibly, I don't know, that's why it's just
I don't have
thinking
any
out
idea.
loud.
There is a possibility, but I'm not familiar with the subject, so I don't want to lie to you.
Yeah, good, good. Any other questions? Okay, let me stop the recording.
Okay.